we're going to go through the process of hypothesis test. When we perform hypothesis test, we always assume the null hypothesis is true. Therefore, we create an SDSM based on that assumption with a given sample size and a given value of sigma. We collect our sample, and then we examine whether results of that sample are unusual. The concept of unusual depends on alpha, which is our maximum probability for making the type 1 error, like sending an innocent person to jail. Okay, and remember, we form our hypotheses, and then we have two decisions. We either reject the null hypothesis, which meant our sample result was too unusual, or we fail to reject the null hypothesis. Our sample result was not unusual. Okay, and we'll get to more of what that means in a few minutes. And remember that the claim is independent of our decision regarding HO. Okay, so it doesn't matter whether the claim was the null hypothesis or the alternative hypothesis. That doesn't matter when you make your decision regarding HO. Okay, so we set up our hypotheses, and then we're going to either reject the null or fail to reject the null. Okay, so let's suppose we have a question, we read through the question, and we set up a null hypothesis that mu equals 140, and the alternative that mu is less than 140. Okay, and in the question, you're able to identify that mu less than 140 is the claim. They tell you that you want to have an alpha value of 0.05 or a 5% level of significance, and we're going to test the claim. Okay, so first thing we're going to do is create the rejection region for HO. Okay, and remember that all stems from the alternative hypothesis. In this case, a less than means we're shading to the left. Okay, so we create that alpha area of 0.05 shaded on the left-hand end. And remember that there's a z-score called a critical number that goes with alpha of 0.05 or has 5% to its left. Okay, and if you use the inverse norm with 0.05 or use your tables, that's where you get the negative 1.645. And remember, on an x-bar axis, we think that the population mean is 140. That's right in the center because that was our null hypothesis, that mu equals 140. We're assuming that that is true. Okay, so now we're going to collect data. So just suppose we know that sigma's point is 8. We collect a sample of 100 and obtain a sample mean of x bar equals 132. Okay, so you read the question and you're able to get this information out of the question. Okay, so we know that sigma is 8. We collect a sample of 100 and we know that x bar from that sample of 100 is 132. Now the idea here is if the sample mean is in the rejection region, it's too far below the center of mu equals 140 and we reject HO. So if we go back up here, if that sample mean of 132, we know that 132 is below 140, so it's over here on the left-hand side somewhere. But the question is it too far to the left? Okay, so what we need to figure out is 132, when you find the z-score for it, is that farther to the left than negative 1.645 is? Okay, so the test statistic is the z-score associated with the sample. Okay, so to recap, we created our null hypotheses and our alternative hypotheses. We have an alpha value. We create our rejection region based off of that information. Then we collect our data. They told us when we collected our data, we got a sample mean of 132. We know that sigma is 8, and we know the sample size is 100. So now we're going to find the z-score that goes with our sample data. And that z-score is just called the test statistic. because we're testing that statistic. Okay, funny how that works. Okay, so if you want to find the z-score, again, with the sampling distribution of sample means, your z-score is always the same idea, always that same formula. X bar, okay, so that's your sample mean minus mu. That's your hypothesized mean for the null hypothesis, 140. Divided by sigma over square root of n, because we're dealing with the sampling distribution of sample means. We're dealing with X bars. Okay, so when you do that in this one, you should have done this several times by now. Okay, and you'll notice when you do that, make sure you keep the 8 and square root of 100 together. Now that turns out to be a nice number, 0.8, because 8 over 10. But when you divide that, make sure you keep that together. In our calculator, what I always do is 132 minus 140, press enter, and then divide by parentheses 8 over the square root of 100 and end your parentheses. Okay, notice we get a z-value of negative 10. Now, what we know about z-scores is that's the number of standard deviations that a data value lies from the mean. So a z-score of negative 10 is way out here to the left. Now notice, we know that it's well beyond that negative 1.645. Okay, so what is that going to tell us? Well, let me get my red pen. And our test statistic is way out here at negative 10. So we know that 132, that sample mean, X bar equals 132, that's way out there to the left of 140. Okay, so this is the grand finale here. What is that telling us about HO, the null hypothesis? That the mean is 140. Well, if we got a sample mean of 132 from a population whose mean was really 140, we're saying that that z-score, or that result, is so unusual, way out here to the left, that that has a very small probability of happening. So that would be unusual to get a sample mean of 132 if the mean of the population was really 140. So what it appears is, it appears that the mean should really be lower than 140 based on the sample that we took. Okay, so what does that tell us about HO? Well, notice how I called this the reject HO region. That's the shaded region out here. So if our test statistic falls in that shaded region, our decision is to reject HO. And again, the reason we're rejecting HO is because our assumption that the mean was 140, in order to get a sample mean of 132 from that population, that would be very unusual, which implies that that assumption was a bad assumption, that the mean was 140 to begin with. Okay, so the decision we make is we reject the null hypothesis. And then what does it tell us about the claim? Well, the claim was the alternative. So if we said that the null hypothesis was no good, so we're rejecting that mu equals 140, then the alternative, mu is less than 140, is good. So we are going to support that claim that the mean is less than 140. Okay, again, the sample mean of 132 would be unusual if the mean really was 140. So we're saying that the mean should be less than 140 in order to get that 132. Okay, so there's enough evidence to support the claim of mu less than 140. Okay, moving on to the next one. Okay, I'll go through these a little bit quicker. So using that same information as an example 1, now suppose the sample mean was X bar is 138. So rather than 132, which we knew was way below 140 based on the distribution, now suppose we get a sample mean that was closer to 140. It's still less than 140, but it's closer to 140 than 132 was. So now, if that's all that we change in the information, now what is our decision about HO and what's the claim? Or what decision do we make about the claim? Okay, so your hypotheses, you set them up very similar. Mu is 140, mu less than 140 is the claim. That's your alternative. Alpha is still 0.05, we're not changing that. Okay, and then your rejection region is still the same. If you go negative 1.645 standard deviations below the mean, that's what has alpha equals 0.05 area to its left. Now we collect the data, and this is what happened. We got 138. So now, on our axes, where is 138 compared to 140? We know it's to the left. It's not as far left as 132 was, but did we get close enough to 140 now that we bypassed that negative 1.645? Well, let's see. Your test statistic, okay, we just changed that to 138. Everything else was the same. And we get negative 2.5. Well, that is still out here to the left of negative 1.645. So even though it seems like 138 is close to 140, based on the variation in our data set with the SDSM, the X-bar distribution, it didn't get close enough. So we have the same decision that we did before. We reject HO, and we support there is enough evidence to support the claim that mu is less than 140. So that one, the decision was exactly the same because our test statistic was still in that rejection region. Okay, last one. Take a wild guess what's going to happen on this. Now let's say we take 139 for a sample mean. So everything else being the same, except now we take a sample of whatever the size was, 100, and we get 139 for the sample mean. Well, that's going to be closer to 140 than 138 was, but is it close enough? Well, create your hypothesis, same as before. Rejection region, same as before because alpha didn't change and your hypotheses didn't change. But now your test statistic, 139 minus 140 over 8 over square root of 100, is negative 1.25. So now that test statistic is right in here. Okay, well now notice that we are to the right of negative 1.645. So we are no longer in that rejection region for HO. Well, remember, the two decisions are to either reject HO or fail to reject HO. Well, if we're not in the rejection region, we are going to fail to reject HO. Okay, so there's our decision. And what does that mean about the claim? Well, now this is a little different. The claim was still the alternative hypothesis, but now we are failing to reject HO. So we are saying that mu equals 140 is good, which means the alternative, not good. Okay, so if you fail to reject HO, that means there's not enough evidence to support the claim that mu is less than 140. Okay, we're not rejecting that mu is less than 140. We just cannot support that the mu is less than 140. Okay, so essentially what that's saying is the 139 was close enough to 140. So if that population mean really was 140, it is not too unusual to get a sample mean of 139 based on the sample size and the variation in that X-bar distribution. Okay, but 138 was unusual. 132, that was way too unusual if the mean really was 140. Okay, so that's the idea, or the general concept of hypothesis tests.